welcome back all of you for the second seminar of today, that it will be given by Miguel Mendez, a name that, as you can all imagine, is Italian, because Miguel is Italian, and is from Karman Institute, and is working on fluid dynamics, and in particular on how to integrate machine learning and fluid dynamics. That will be the subject of today. So Miguel has very recently won an ERC grant, and is also teaching from time to time at ULB in some courses where we teach together. So I was, when we decided about the theme of the year, he was one of the first person I thought about for an invited guest here at BrIAS. So without taking too much time more than that, I give the stage to Miguel for his presentation.
Hello. Thank you very much, Emanuele, for the introduction, the invitation. So indeed, I'm going to talk a little bit about methods to integrate machine learning in fluid dynamics engineering. I'm particularly picky on the word engineering in the sense that we are going to really focus on applications. So it's really an application-oriented talk, let's say. But to understand, let's say, how to integrate them, I will start really from the fundamentals, starting from a general framework defining what we mean by machine learning. And so building on that framework, we will look for ways in which we can plug things that we know. So let's say the traditional engineering methods, let's say. And then I want to show you some case studies. I picked 4. Let's see what the times allows to talk about. They are very, very different kind of problems, experimental, numerical problems. I will just to show you, let's say, an idea of how to use these principles, let's say, and then finally wrapping up with some conclusions. So, what is machine learning? Now, this might seem a silly question to this audience, but I think it's important to have the general framework. So, okay, we all know that it's a subset of artificial intelligence dealing with the idea of learning. And when we talk about learning, there are different definitions. The one that I like the most is the one by Tom Mitchell in his book from 97. Who defines learning essentially as an optimization process. So we need some experience. So we say that a computer program learns from an experience with respect to some tasks if some performance measures, P, improves with experience. Okay, so if you get better and better at that specific task. So the ingredients are experience, task, and performance. And of course, in computer science, these 3 are very, very different from the ones that we have in engineering. Now, in a very broader sense, so the task that we have somehow to solve can be seen as a function, right? So learning from a certain target domain to an output domain. This can be in input, say, images, in output classification, or continuous functions, you name it. Experience means data which we use for training and for testing. And then, not directly mentioned in the definition, but somehow you have to encode this function, okay? So somehow you need some sort of function approximator, which here pictorially I will represent with this agent, let's say. And I am going to picture it as a parametric function. It doesn't have to be a parametric function, but for the moment I think this is good enough. So this is a function that depends on some parameters. And then you have the optimization, which is the engine of the learning process. So you have some way of measuring performances, if you're doing good or bad. And this performance is based on experience. And hopefully the more experience you have, the more chances you have that your function approximator can approximate the target function, which you don't know how to formulate in the first step. So essentially, curve fittings. This is basically curve fitting on steroids at scales that we were not really trained to digest and to think about. So if I try now to take that framework and really compress it into something a bit easier, I will maybe picture it in this way. We usually have a training phase where this agent is making predictions. These predictions goes into an optimizer, and the optimizer updates the weights by simply checking the performances from that. And once you have the good solution, then you deploy this solution. Now, this is an oversimplification. Of course, training and deployed solution can coexist. I mean, things can go hand in hand, but in a very simplistic way, I will call this the brute force machine learning, the brute force core fitting, if you want. Now, the success of this kind of approaches are quite evident. Image recognition, even generating videos, deep fake videos from images, language models such as ChatGPT, and more recently you start seeing even AI influencers or TV show leaders, which basically are people that don't exist, that are entirely generated by AI. So this gives you a bit a flavor of the power of this core fitting, where it arrived to some extent. If we take only the, let's say, language models, we are talking about, I told you that there is a parametric function that needs to be learned. And if you take llama models, for example, the number of parameters we are talking about is in the order of 400 billions parameters. Okay, so we are fitting things at a scale which we are simply not used to really think. And the number of training points or tokens that you see in ChatGPT, etc., goes in the range of trillions. Okay, so the amount of data, the amount of samples that you have to train this brute force core fitting is something which, in the world of images or multimedia content, it's really, really abundant, and so that explains the success of these ideas. And of course, now it's very tempting to say, okay, how can I use this in engineering to solve really practical engineering problems? And I could not really think of any practical problem where you have that amount of data. Okay, so the kind of machine learning which we need is completely different. It's not purely based on data. I mean, we need to do something else. I will show you some examples later. So what can you do? And that's where some people call it scientific machine learning. I don't particularly like this terminology, but I will stick with the flow here. So the idea is that you take back the framework which I've explained before. So task, experience, function approximator, and an optimizer. And you try to think about ways in which you can plug in physics. And hopefully, the more physics, the more knowledge you put there, the less data you need, and the more you can benefit from the core fitting power, let's say. Not to ask the machine to reinvent the wheel, but somehow complement these powerful tools with knowledge that you have. So we'll say that the first approach obviously is at the level of choosing your physical features. Okay, so you have to choose them cleverly, and here is where the domain knowledge is vital. Okay, you really need to, if you formulated the task wrongly, there is no machine learning miracle that can save you, let's say, from disaster. Another level is at the hypothesis set. So here, in machine learning, we usually think about neural networks. People call these models. In engineering, we will not really like to call these models. Maximum, we will call them surrogate models. But when we talk about models, we think about something else, right? We usually think about some equations which are formulating a physical principle, conservation laws, and et cetera, et cetera. So the least we might want is that maybe these prediction from the pure machine learning model either are solution of some equations, or maybe they just offer some part of the term in the equations that you don't know. Okay, you still keep the rest of the framework already there. I will give you some examples there. Again, here, that's really an art. You need a lot of, let's say, know-how in general to have a good integration between the two here. And the other approaches is, on the other hand, to go on the learning step. So you can go here in two ways. One way is to penalize things. You can penalize an algorithm for violating certain principles, and this hopefully will push the algorithm to choose certain solutions. So you can add a penalty. Or you can make it more complex and add a constraint. Okay, now an optimization problem in this setting is usually sufficiently difficult. If you also add hard constraint with Lagrange multipliers, etc., things can get usually very difficult. But that is also one way to force let's say, the machine to respect things that you know. So I'm going to show you some example of each of these methods, and of course combinations of these ideas as well. And the first one, well, how many of you are in fluid mechanics? That's a good sample. Well, in fluid mechanics, one of our biggest holy grail is turbulence modeling. Okay, it's an unsolved problem. We spend decades on turbulence modeling. We still don't have a good turbulence model, and we probably will never have a very good turbulence model. And trying to do this with machine learning now is a big topic on its own. So when we talk about turbulence modeling, what do we mean? Now, without going too much into the details, I just want to give you a flavor of what's the idea here. Usually we have an equation that governs perfectly how our flow evolves. That's Navier-Stokes equations. And we abandon the idea that we can solve for everything which is happening in the flow. We say, okay, some parts of things we're going to solve for, other things we're not going to solve for because it's too demanding, computationally speaking. So we introduce a decomposition in the equation. We say this part we're going to solve, this part we don't want to solve. And because the Navier-Stokes equations are non-linear, the things that you are not wanting to solve bring a new term in the equation. And we say the problem is unclosed because this new term, you don't know what to do with that, essentially. Okay? So we talk about closure in the sense that we want this term to be linked, so the things that you don't know to be linked to the things that you know. Okay, that's the closure. And of course, that's where thinking of an artificial neural network or a machine learning algorithm to find the closure is a very natural thing to do. There have been tons of models, so there is a big field on turbulence modeling on finding this closure based on physics, but they all involve a huge amount of empiricism of coefficients that you have to tune, 0.09, maybe 1.67, etc., etc., etc. We hope that at least the machine can help us doing this. And if we take now the thermal problem, so that is the case of an isothermal problem. If you take a thermal problem, you end up in a very similar setting. You have an equation that describes how energy should diffuse or be advected in the flow. But again, you have terms that you don't know how to handle, and again, you fall in the problem of closure. Now, here I'm talking about turbulence modeling because I come from fluid mechanics, but the idea of closure is something which is present in almost in many other engineering contexts, let's say. And I'm talking about that because I want to show you an application. This was a work from a PhD student, Matilde Fiore, on physics-constrained machine learning methods for thermal turbulence modeling. And in her work, we were interested especially at low Prandtl number fluids, so liquid metals, to make it concrete. So in liquid metals, what you have is that the conduction effect can be so strong over the advection effect that traditional turbulence models don't like this. So it's not a standard settings, let's say, for turbulence modeling, and there are not so many existing turbulence models that can handle the situation. So she spent a lot of time trying to make it work. It was quite a failure to try with brute force for many reasons, but the main root cause is, again, the lack of data. I mean, we don't have that huge amount of data which I've shown for the brute force approach. So we finally end up with this architecture where first you enter with a very carefully chosen set of physical features in your model. So that is somehow a way to construct and to embed the Galilean invariants. So we all know that if you do a computer simulation and you change the position of your axis, the solution should not change. But to teach this to a neural network, apparently you need a lot of data, okay? Which we don't have. So somehow, if we know that, let's try to find a way to enforce this to already happen. Then more architectural constraints. So we know that heat goes from high temperature to low temperature and not the other way around. But again, to teach this to a neural network, you need an horrendous amount of data to make sure it assimilates this idea. But we know it, okay? So why don't we try already to enforce it somehow? In turbulence modeling, we call this realizability, because if you violate this principle, then a lot of bad things happens. And then somehow we don't want the network to do all the job. We have very powerful CFD solvers that can already solve Navier-Stokes equations. So we want to keep those things. So somehow we want that our artificial neural network interacts with an existing solver, OpenFOAM in this case. And you have to make sure that they don't fight, which is also something that usually happens because, for example, numerical methods don't like to have sharp peaks or gradients, otherwise numerical stability suffers. So somehow you have to tell the neural network that it has to predict something which we like to call smooth. Now, how smooth, that's another story, but somehow we want to make sure that the interaction between these guys is sufficiently robust. And so the architecture that she came out with is this one. It's fairly complex, but I want you to get a bit just the flavor of what are the components there. And I will start from the end. Okay, so here we want to predict turbulent heat fluxes. We know from physics a reasonably good law, Fourier law, or somehow a generalization of the Fourier law that tells us that this could reasonably well modeled with a linear relation with respect to the gradient of temperature, and that linear relation comes from the dispersion tensor. Now, this dispersion tensor, if you want to make sure that it goes from high temperature to low temperature, needs to respect certain conditions. So in this architecture, you cook up the dispersion tensor from other two tensors, a symmetric and an antisymmetric part, which are built in such a way that you guarantee that all the eigenvalues respect the properties that you need to respect. And what the neural network is asked to predict are, so we write those symmetric and antisymmetric part as a linear combination of other tensors, and the neural network has to predict the coefficients of the linear combination of those tensors. And what are those tensors? Well, those tensors are carefully cooked up to respect scaling laws and Galilean invariance. These are built from the velocity gradient tensor, and they only contain dimensionless quantities, so you respect the scaling laws that somehow guarantee by construction that you are going to respect the properties which we talked about. So basically we did most of the quote-quote heavy job of ensuring certain things, and then we let the neural network do the dirty job of tuning those coefficients. And here we were, so then we had also penalties. As I said, this was combined with the CFD solver, so you had penalties to ensure that the predictions are sufficiently smooth, and the results were quite surprising. I mean, this network was trained with relatively few datasets, but it achieved very good comparison with DNS or with the full Navier-Stokes simulation in relatively complex situations. At a fraction of the computational cost of running the full thing, let's say. And more recently, we even start checking ways in which you can train this network with different levels of fidelity, because it turns out that that you can train such a network to recognize whether he is going to be paired with a low fidelity CFD or a high fidelity CFD and adapt its predictions accordingly. As a second example, I'm now go to aerodynamics, so flapping wing aerodynamics. Some of students were really obsessed by flapping wing drones, or flapping so birds, so natural flappers, such as an hummingbird, for example. They have very remarkable skills. I mean, they can hover very stably. They can do a lot of very cool things. So there is an interest in building, in imitating them, and somehow build very small drones that can be used for various applications. So here we start really from. So what is the goal here? We want to have a model that very quickly predicts the aerodynamic loads on your flapping drone. Okay. There are existing correlations which we take as a starting point that can tell you the dimensionless lift and drag forces, so we call them the lift and drag coefficients there on the right, as a function of some dimensionless quantities. I'm not going to go into the details, but you should know that these things can be predicted under certain conditions, and mostly the conditions are conditions of relatively gentle flapping. Okay, so if you flap in a relatively smooth way, let's say the aerodynamics is still complex but still digestible. But if you start doing very aggressive maneuvers and you trigger separation and more complicated things, then there is no way you can actually predict precisely what is going to happen. Of course, you can do CFD simulation for this, but one CFD simulation of this, it's really, 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 really expensive. So in this project, we were thinking about ways to try to use machine learning to have fast prediction or surrogate modeling if you want. And again, here the problem of a lack of data, which is basically what we always encounter in our life as engineers, forced us to think about architecture which are, let's say, cleverly designed. And here we went for what we call a multi-stage regressor. So you have one regressor which is taking certain features from physics. It's a parametric function. Here we put a lot of physical constraints, and then somehow during the training process we have a second agent that has to find the parameters of the first one from other operating conditions. So here there's a combination of physical features and architectural constraints. And then once you have to make predictions, these two guys have to work together to give you the prediction, let's say. Now, just to give you a flavor of how this looks like. So Mr. M1, so the first predictor, has to predict the lift and drag coefficient as a linear combination of some bases. These bases are in the vector B that you see there on the bottom. These are function of two angles. These are the flapping angle, phi, and the pitching angle, alpha, that controls how you are tilting your so somehow this controls your kinematics, okay? Which can be aggressive or less aggressive. Now, some of these terms, the first one, for example, can be expected from potential flow theory. So there is some physical flavor there. Others a bit less, but you could add them to allow the system to have some sort of hysteresis, which you might need in case of aggressive maneuvers, and so on and so forth. So somehow this is a basis which has been cooked up wisely. Truth to be told, I wanted to have less terms, but the students wanted to put more. I think at the end it was not too expensive, but so you have first to guess the coefficients of this linear combination. So here it's purely kinematics if you want, and now Mr. M2 has to predict the coefficient of the first guy from other conditions such as Reynolds number and other dimensionless parameters that define how aggressively you are flapping or not. And now for this M2, we use a Gaussian process regression, which is a very standard tool in machine learning, which has the cool advantage of giving you also reasonable guess for the uncertainties. And these uncertainties can be propagated to Mr. M1 quite easily because Mr. M1 is linear. So you have a model that very quickly tells you not only the prediction, but also the uncertainties. And now you can combine these uncertainties with another optimizer and use it to do what we can call self-learning. So where do you sample next? I can sample in the next point can be taken in the input space such that I maximize the amount of things that I learn. So how much I can minimize the uncertainty if I sample in that specific point. So that's a lot along the line of kriging or Bayesian optimization if you want. So this was trained with only 165 simulations, which took approximately 4 months to run. And of these, I don't want to say something bad, but maybe of the order of 150 were chosen by the students, and the rest are chosen by the algorithm, let's say. So you have a self-learning guy, and that's pretty good. It's not too much work. We didn't do that, but you can imagine that you just show the algorithm how to prepare your OpenFOAM simulation and then just even run it, and you can maybe launch this in September. You come back next year and maybe has done under 20, 30 simulations and has learned something out of that. Now, these are some predictions in out-of-sample conditions, so 5 test cases which were not in the training set. On the top, I'm putting the 2 angles that controls the flapping. So the first one on the left is a relatively gentle flapping. The others have some sharpness either on alpha or on phi, so they are doing some more aggressive maneuvers if you want. And below, I put the lift and drag coefficients within one cycle, from the CFD, from the Mr. M1 when it was working alone, and the combination of the two. The bottom line that I want to say is that overall it works, otherwise I will not be showing it, of course. But what is nice is that also in terms of uncertainties was quite okay, and it's working quite well even in relatively aggressive maneuvers. It's suffering a bit the case 3, the one in the middle, because there I think we really pushed the boundaries. There is really a separation effect that cannot be well represented by the bases which we have used. But okay, learning from there, we could maybe modify the bases to have some spiky behavior near a ramping up, let's say. Example 3, now we go back to the lab. So experimental fluid mechanics, and in particular image velocimetry. So this was a project for galvanizing lines. So imagine that you have a plate. I don't know if I'm going to use the mouse here. Well, maybe not. Okay, so I'm showing you some image velocimetry data obtained in the lab. So what we have here is a large cylinder which is rotating inside the butt and is simulating a strip which is immersed in a butt. That's what you find in galvanization line for coating applications. So on the bottom right, you can see an animation with the kind of measurements that have been obtained. So here the idea is that you have 2 cameras. In the liquid, you put small particles that can follow the flow, and you illuminate these small particles with a very sharp laser pulse of the order of 10 nanoseconds, such that you basically freeze their motion and you see the particles one by one. I tried to show you on the bottom video where you can see this particle moving, let's say, in the flow. And the upper camera is, on the other hand, recording the interface, and then there's some image processing to find this interface, okay? And then there is some image processing to put the 2 informations together, such that you know where the interface is and you know what is the flow there. Now, this in galvanization, it's a very important configuration, because what can happen is that if your strip goes at a certain speed, usually the strip is not perfectly flat. There is always some level of roughness. You can entrain air because the contact line is not stable, and this air can remain on the plate if the bubbles are sufficiently small and come back when you pull the strip out of the butt and create defects. So here the idea was to study how this process is happening. Why do we need machine learning for that? Well, the kind of measurements that you have here, as you can see, those black points are very punctual. So that's, you have velocity value at each of those points where the particle is, but you also see a lot of white areas where you don't have information, okay? So we would like to have a better representation of these flow fields. And so the idea is to do some sort of quote, pass the term, clever interpolation, if you want, or we call this super resolution, where we get an analytic representation of this flow field, which we can sample anywhere, but we want to impose, again, things that we know. For example, we know that the flow field should be solenoidal, because this is an incompressible flow. We know that at the wall you should have a slip condition. We know that at the interface there must be a kinematic condition that links the displacement of the interface with the displacement of the flow underneath. So we know pretty much a lot of stuff, let's say. And the idea is to inject all of these things inside the regression before you get this full reconstruction of the velocity field, but then also pressure field, and also things that, let's say, you're not measuring. We're not measuring pressure here, okay? We're only measuring velocity. Now, again, we know a lot of stuff about this. If we take the case, this is a liquid, so it's incompressible, we can use these equations to infer things directly from this kind of measurement. So here, we went for a full learning constraint approach, so using Lagrange multiplier, and then the predictions are simply, so here the model was not coupled with CFD or anything like that. Okay, the model was supposed to give already the full flow field and the full pressure field, etc., etc. So to do this, we used radial basis functions. So imagine the idea is that, so again, you have a situation like that, scattered data, which is noise, of course, which is very sparse. In some areas you have a lot, in some areas you don't have at all. And from this, you want to get also unseen quantities, for example, pressure. Now, pressure is linked to the velocity through an equation, which we know, it's the Poisson equation. And the idea is to use this data and enforce the fulfillment of this equation to obtain, in one shot, velocity field and pressure fields, for example. So we do this with radial basis functions. So we write velocity and pressure as a linear combination of some bases. If you inject this into the equation, what is particularly interesting is that you have a problem that can be kept linear. So the solenoidal condition is a linear condition. The pressure Poisson equation is linear with respect to P, not with respect to U, but it is linear with respect to P. And to enforce a bunch of important constraints, I mean, we can write them as linear constraint. And the radial basis function expansion is also linear with respect to the weights, meaning that we can really put hard constraint, not penalties, but hard constraint, relatively easily. So I'm not going to go into all the details, but this is really traditional constraint optimization where you have a quadratic, and that's why I was insisting that I pick always linear constraints or quadratic penalties. But what happens is that you can solve, you arrive at a system of equations which is linear, which is a canonical form that we know how to solve out of the shelf, let's say, which will give you the solution of the weights, at the same time the Lagrange multiplier that you need to fulfill the constraints, and so you respect directly the constraint, and then you can plug this also in the pressure reconstruction and do the same game. So this was work with Pietro Sperozzo and now by Manuel Ratz, who is pushing this also to 3D. So what you see on the bottom right is a 3D reconstruction of the velocity field. And keeping this philosophy of linear thinking, now Manuel is also implementing constraint based on the turbulent transport of equation. But you can obtain, let's say, full reconstruction of the velocity fields from the sparse data. There is an open source code, but I go for the last application, digital twinning. So I think this now is a buzzword that we all hear a lot. And somehow that's also a way of combining physics with machine learning models. So really big picture view of how, let's say, you can frame this digital twinning idea. Well, you have a model, which we represent in this way. So we have a physics-based model. So imagine you have a dynamical system which depends on some state variables S, and the function governing this dynamical system is coming from physics. Okay, so this is purely physics-based. But inside this physics-based law, you have some terms that you don't know, that you cannot really model from physics. Okay, think about mass transfer coefficients or drag coefficients or things like that. So that's where you want to inject the empiricism, and it is in this empiricism that we will put this machine, let's say, to try to complement. And the idea is that if this machine can close your problem, then you can obviously use traditional numerical methods to advance your system, let's say, and you have quote the perfect synergy, let's say, between the two. Now, the architecture here is, so imagine you have some pi groups, so these are dimensionless groups in the fluid mechanics terminology, so somehow you have a closure that has to then enter into a physical model, which is usually implemented with an ODE, and then somehow the optimizer has to take into account the interaction between the two. Okay? And what we call digital twin is that part on top where, so this combination of the closure and the physical system. Why we call this digital twin? Because this is to be tuned and to be adjusted on a very specific system on the fly, okay, while the system is running. And if the system is changing because maybe something is changing, the optimization keeps on going and sees that things are changing, for example. So the way we put it is a bit like reinforcement learning style, if you want. So instead of talking about a control agent, you have a modeling agent. So the goal of the modeling agent is to predict something on the system, okay? So it has to predict the evolution of the system, and it is continuously informed by the current state of the system. And the predictions depends on the parameters that you have in the closure, okay? So you have some way of measuring whether the predictions are good or bad, and you have some ways to compute the gradients with respect to that. Here, if you're familiar with this, the idea is to use the adjoint methods to take into account also for the physics in the system. And this is continuously updated. That's a bit the philosophy. So if your system is changing, the optimization keeps on running all the time. And now you don't have to do this only for one system. imagine that you have many systems that are similar. So somehow some way of parallel computing in the physical world. Instead of sampling only from one environment, you sample for many environments. Maybe one of them is here, another is, I don't know, in US or whatever, you see. So it doesn't have to be, it can be distributed philosophy a bit, as we have also seen before. And so from each of these, then you have different ways of evaluating your global cost. So you can have simply an average, or you might, for example, see that one specific environment is behaving very differently from the rest. So maybe there is some anomaly on that system. So you might want to keep that system out of the training because something happens there. And this might even tell you that maybe it might be a good time to go to do some maintenance to that element and so on and so forth. And that's a bit the topic of my ERCs, where we also do control on the systems. So we target systems that are, let's say, composed of many elements that are similar. So think about float of drones or cryogenic storage units or wind farms, for example. These are all cases where you have many components which are expected to behave in a relatively similar way. I close just with one example that was a proof of concept for cryogenic storage units. So imagine that you have a tank which contains liquid hydrogen. So we are at 20 Kelvin, so very, very, very cold. And you know that because of the very low temperature, no matter how good your insulation is, somehow heat is entering and pressure will rise up, will keep on rising. So you have to do something about that, and you should hopefully do it in a clever way, not to waste too much energy. And the thing is that we learn almost in high school, no, not high school, but in classic courses on thermodynamics how to model this system. So it's a balance of energy and the balance of mass between various control volumes. But these kind of models hide the complexity in the heat and mass transfer coefficients between the various systems. So imagine that you have vapor and liquid, and somehow there is an evaporation. So some of the mass in the liquid has to go into the gas. So we know how to express conservation laws. That's not something that we want to give to a machine learning algorithm. But how much of that and how that is linked to the state, that is where the machine learning can help. So here is an example of a very simple three control volume approach. We have just one control volume for the ullage gas, one for the liquid, one for the walls. I don't want you to focus on the details, but on the terms which I'm putting in red, these are the ones that you don't know really how to learn, how to model. There are empirical correlations which work for a specific setting, for a specific scenario, but once you go into the wild and you have already deployed your system, these correlations don't really work, and they might even depend heavily on the kind of system that you have. So the idea is to learn those terms on the fly, okay? So in this work, we tested various, so physics-based and using machine learning methods, and the question was to see to what extent and how quickly and efficiently could the machine learning find back the correlation that we were putting to model the system. And so the architecture looks more or less like this. You have, this is your real tank. You take some measurements from this tank, for example, pressure and temperature. You have your digital twin, which is trying to predict that pressure and that temperature, depending on some parameters, heat and mass transfer coefficients. So you simulate the measurement process for what we can call an observation operator. And all of this goes into this agent somehow. This agent has a buffer memory, like in reinforcement learning, where you are sampling. And it has an adjoint-based solver that can evaluate not only the cost of, the performances, but also the gradient with respect to the performances. And then there is an optimizer there that keeps on going on forever with the system. So eventually, at some moment, this agent will learn well how this specific tank works, let's say. So this is an example of testing that we did in this work. So here I'm showing you some simulations for a tank, which is undergoing various scenarios. So the most dangerous one here is sloshing. So imagine that this, for example, is in a boat and there is some wave and you have a sudden increase of heat and mass transfer between the two control volumes. This usually produces a huge pressure drop. That's why people wants to control this as much as possible. And here in this environment, it's a virtual environment where these events happen randomly. And the question is, how much time does it take for the agent to find this bug? And how much does it feel, for example, the impact of measurement noise in your system? And here I show you 3 examples. One case is with the clean signal and then different levels of noise. So on the top you see pressure, then temperature in the vapor and in the liquid. What we found out is that within reasonable amount of noise level, well, noise is not just not a problem, but it is actually something quite helpful in the sense that it helps escaping local minima. And we see that an agent of this kind can reasonably quickly learn within, let's say, what we can call real time, I mean, useful time of the order of minutes for a tank of this kind. And then in the paper, we show also what happens if you have an agent that is only interacting with one tank, or maybe with 2 tanks, or maybe with 3 tanks. And what you can expect is that it learns much faster if, of course, it's sampling from different tanks. Okay, I think that was largely sufficient, maybe a bit too much, but so I will conclude with a very general thought, let's say, at least the main impact which I see now of this machine learning engineering. So far we've been used to see machine learning more as something of computer scientists, the brute force, give me enough data and I will tell you everything you need. And on the other side, we've been always looking at people saying, no, I'm a physicist. I don't want to rely on data. I can derive my models which generalize, and I can do this in my office. And then I have computers to solve the equations which I'm going to derive from real life. So I'm going, of course, to take inspiration from nature, but somehow I don't want this brute force. I've been always looking at this as somehow very different words, let's say. And I hope that now with these 4 ways that I talked about, I convince you that it doesn't have to be black and white. You can introduce a lot of physical constraint and physical knowledge into the machine learning process and then benefit from that. That's it. So thank you very much for your attention. If you have any questions, I will be very happy to take.
So, are there questions?
Hello, thanks for the talk. And my question is, since there are many ways to integrate the physics in the models, from hard to soft constraint and where to put them in the model, from your work, do you think that there is one way that is better than the others, or it just depends like on the problem you're working on?
It really depends on the problem you're working on, I would say. And also, I would say that they are not all, quote, quote, equally easy to implement. So I number them from 1 to 4 because I usually want people, I mean, my students mostly, to start from 1 and then go to 4. In the sense that 1 is usually relatively simple and can give you, let's say it's a relatively low-hanging fruit most of the time. 4 can be very difficult. So, for example, 4 is not usually applied in neural networks. I mean, now we see a lot of physics-informed neural networks which are using 3 because 4 is really difficult in that case. So, in general, start from the low-hanging fruit and you will be already surprised by how much you can get from there. And then if you can go down to number 4, then let's go.
Thanks.
Thank you.
Other questions?
Hello, thanks a lot. It was a very interesting presentation. At a certain point, I understood you mentioned that noise actually helps scaling up local minima or something like that. Could you elaborate on that? I couldn't understand.
We noticed this in this test case of this optimization. So if you take this specific test case, for example, we were using an Adam optimizer, so gradient-based optimization with the gradient coming from the adjoint. And the cost here is measured by, so performance is just an L2 norm measurement of the prediction of the system versus the noise, versus the data that you have collected, let's say. And what we have noticed is that, okay, you can put momentum in Adam to try to escape local minima and so on. But what we have seen, I don't have a plot for that. No, I don't have a plot for that, unfortunately. But what we simulated is imagine that I'm sampling, in my observation operator, I have no noise. So the temperature and the pressure which I'm measuring is exactly the one that I'm supposed to measure. Or I put a little bit of noise. I don't remember if it was 5% or 10%. And if you look at the cost function, the way it was decreasing, you find that actually 10-ish% was actually making go down more easily. We don't have a formal explanation for that, but it might be due simply that somehow it is as adding an extra inertia, let's say, in the downhill process. Thank you.
Other questions? Well, if not, I have actually one.
Yeah.
That is so. I actually, that's something I keep repeating, that when we speak about what it's called AI with a fantastic, which is fantastic marketing, I must say. At the end, it's about going back to optimization and solving badly an optimization problem that we cannot solve. So when you were showing that the slide with your 4 or 5 points, and the last one was about embedding actual constraints, I would say that the main problem is really there. It's in the basic optimization that we use to train these objects, because those are basically simple gradient descent of some sort that do not account for constraints. So this is something I say quite often, that it's one of the problems. You are aware of some research in that sense?
I have seen some works on trying to, let's say, boost physics in neural network with constraints. So but that is more a philosophy where you want to use a network to solve an equation. And so somehow you can formulate using standard methods from optimization based on an augmented cost function that somehow, and then you have to solve for these extra lambdas. But training a neural network is already a sufficiently hard problem. When you add the constraints, you have to imagine that you will have one extra lambda for each constraint that you are putting. So it becomes much more complex. So I've seen some of this in the field of using neural networks to solve equations, but I've not seen a general, let's say, a general approach to that.
Okay. And a question instead about one of your last slide, and then I don't know if there are other questions, otherwise we will end here for today. So in the last thing that you were showing us, you were using several models in parallel to try to learn something. At the very same time, there is one aspect when you have all these similar systems in parallel, is that each one of them is actually subject to different phenomena, and over time it is normal that all the parameters diverge, because aging is different, for instance, because uses is different, and so on. So the risk isn't it to learn an average model that maybe has no meaning in reality?
That's absolutely an open question. Yes, indeed. In this case, you are letting, let's say, the average man, the average wind turbine in the system. But I will say that the benefit that you can have from sampling more can overcome this limitation if handled sufficiently well. Because it's true, you have an average model to some extent, but you have also, let's say, departure from the average. And you might have, for example, that turbine number 3 was very well aligned with the average until yesterday, and now today is not. So maybe something happened between yesterday and today, and I can decide to isolate that from the learning process and maybe treat that separately because of that. So indeed, this is something to take into account, but I would say it's more a research avenue than a problem. Although
Okay.
maybe these are synonyms, but
Okay.
to be investigated.
So if there are no other questions, I would thank again the speaker.
Thank you very much.
And with this second speaker, we end here the formal part of our Thursdays at BrIAS. I mean the formal part because our Thursday does not end here. As usual, you are invited to take a coffee, to take a seat, to discuss, to have a crazy idea, to make comment that might seem stupid, but it may be open new avenues to thought, and so to enjoy the rest of the afternoon with us. So have a good day, I also say bye to the people that are listening to us online, and see you next Thursday.